Okay, so let's begin. We want to look at discrete event modeling, looking at that's discrete Markov modeling. Okay, and as you are aware, I sent you the notes last week, so I expected you to look at it before coming to class today. So I'm going to play the video. Listen attentively. If you have any questions, please let me know it. I'm on standby here. Okay. Okay. Yeah, so discrete Markov chain modeling. Our goals for today, or the main things we are looking at today, is to understand what stochastic processes. I think we've looked at that, but we'll refresh our mind what stochastic processes are, to understand the Markov, the property, and also to look at the applications of Markov chains and how analysis and modeling is done with Markov chain. Okay. So what is a Markov process? We looked at a Markov process the last time. We said we can have two types of Markov processes. We can have the DTMC, that's a discrete time Markov chains, and then a continuous time Markov chains. Okay, good. And we also look at the time steps or the time intervals within which occurrences or arrivals occur in discrete Markov modeling process. Okay, and then we look at what a stochastic process is. We said a stochastic process is a random variable, okay, which has a set of values that form the state space. Okay, so for example, in modeling the weather pattern, we could have two possible state values, which are sunny and a rainy day. Okay, and we said we can write the stochastic process or the random variable, okay, as the weather pattern, and the state space of that system will be a set containing sunny and rainy weather. Good. Then we defined the Markov process as a process, okay, which, okay, follows the Markov property. And what we refer to as the Markov property is a state of event or a process which does not depend on past event, but only on the current. Okay, more or less the memoryless property. Okay, so a Markov chain is basically a discrete time stochastic process with a Markov property. Yeah, and then we also mentioned that in Markov modeling, all we need is what is happening today, at present. Okay, so illustrating with this diagram, we said if we have to model what is going to happen tomorrow next, then all we need are the one-time transition probability, okay, on day 5. Okay. Okay, so let me touch on this briefly. Okay, so when it comes to Markov modeling, we are saying that a Markov model is a stochastic process which does not take into consideration what has happened in the past. It only relies on current states or current probabilities of various events. Okay, and based on what is happening currently, presently, we can predict what is going to happen in the future. Okay, so a typical example will be, or a typical application of this Markov chain is used on web searches, okay, web engines, and basically YouTube and all that, YouTube, Google search, etc. So for example, for a demonstration, when you go to YouTube today, let's assume it's your first time you are using YouTube. Once you get to YouTube, okay, there are a number of videos you are likely to be looking for.
Okay, so if you select a lecture video, maybe on stochastic processes, and you keep selecting related videos to stochastic processes, what happens is YouTube saves your search pattern and looks at the probability, okay, of you selecting a stochastic model notes as compared to notes in other fields. Okay, and then what will happen is in the next transition or the next time you visit YouTube, YouTube is going to focus based on the Markov modeling tool. Okay, it's going to focus the chance. So it comes as recommended search, okay, or recommended videos you like. Because it has estimated the probability for you to like that particular video. Okay. These are some of the applications. So in Markov modeling, all we need is what happens today, okay, regardless of what happened yesterday, and then we forecast into the future. It could be the next event or even the 100th event from today. Any question on that point? Any question on that point before we move on?
No, sir.
Okay. So let me quickly link up. I think the video will do its own work, but let me just touch on some few things. Okay, so in random variable, we said that, or in modeling, we always said that there is a state of the process and there are states, okay, conditions, okay, within the state space, and then we have the states, okay, conditions within a modeling of a system, okay. And in the same way, when we look at our earlier probability models, okay, you find out that we're writing PR of the random variable x, where x is equals to 0, okay, a state 0 when, okay, given x belongs to what? X belongs to this possible state, which is head, head, head. Okay, if you remember from the very beginning of our probability distribution, 1 if x belongs to a certain, okay, condition, and then 0 otherwise, something like that. 2 if x belongs to head, 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 and so on and so forth. Okay, it's the same thing here. So within this context, we are writing PR of x, okay, is giving us this time the state x is equals to the value 0, okay, given that a certain condition, okay. Then here is a conditional probability. So state x at the next day, okay, given the state is equals to 1 at the previous time. So in basic term, if we are relating with the toss of a coin, then this would be interpreted as the state in the second toss of the coin, okay, is equals to 0, which means a tail, okay. Given that in the first toss of the coin we obtain what? A head. So the state now is equals to 0, given that previously it was equals to what? 1, okay. Or the state tomorrow is equals to 0, given that today is equal to what? 1, okay. So that is a conditional probability. In the same way, we are going to see these notations, okay, in Markov property, and subsequently all notations will be in this form for this particular modeling, okay, tool. Okay, let's continue.
Then we also mentioned the representation of the Markov modeling. Yeah, Kenny, is it Isaac? Isaac, can you hear me?
Okay, so on the Screen is how we represent, okay, the states of the process. Okay, so we say that the random variable at a time, say t, okay, or the random process at a time step k, okay, or yeah, then we say it's equal to a certain value, okay. So if the possible values are 0, 1, and 2, then this will be equal to 0. This 0 here represents the small x of k, okay. That is how it is. So if the possible state, if it's a weather forecast, okay, we forecast weather based on Markov modeling tools. So if it's a weather forecast, then it means that the states of the process, the weather forecast is your x, and the possible states of the process will be what? Sunny and rainy day, or sometimes it can even be what? Sunny, rainy, and cloudy, depending on how you are modeling. Okay, which means that the state today, x, today, t, anytime you see t, we are talking about today, okay, could be a sunny day, okay, good. And then the state tomorrow, if we are talking about tomorrow, it will be t plus what? T plus 1 may be equal to what? A cloudy day, okay. That is what these terminologies essentially imply. Okay, so let me clear and play the video.
Yes, sir.
Very well. Okay.
Yes, sir.
Okay, good. Yeah, so we had the random variable at a state time or state space t, okay, or we can also write x subscript k, meaning that the random process at a time step k, okay, has the value small x of k. So sometimes we can represent small x of k as I or j. So I can be the state space, the value of the random process at a particular time. Okay. Then we looked at how to represent this. We said that the probability of the process in a future state, which is k plus 1, okay, being equal to, let's say, I or j, given that the state today is in a certain state, xk. Xk can be I or j, okay, good. And previous given states can just be expressed as the probability that the process, the stochastic process, or the random variable tomorrow is equal in a particular state, given that the process today has a certain value x of k. Good.
Okay, so if you study carefully, we are still talking about the same thing. And we are saying that because the Markov chain is independent, writing it this way means the probability tomorrow, okay, k plus 1 is tomorrow, having a certain value. So it could be sunny day, okay. So the probability tomorrow being sunny, given that the probability today is maybe rainy, and yesterday, okay, so yesterday, the dot 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 means we are dealing with yesterday, which is k plus x at what? K minus 1, okay, x at k minus 2, all the way to the very starting of the process, okay. We are saying that because in Markov modeling, we are only looking at what is happening today, which is what is happening at what? Xk, okay, to predict what is going to happen tomorrow, okay. All these events are not necessary for prediction, okay, which essentially means that we can cross all of them out, and that should give us a very simple probability model, which is what? that the probability of X, the process tomorrow, okay, given the probability of the process today. Okay, good. And then again, you notice that we are dealing with equal to, which means that we are looking at discrete events. Okay, but if you look up here, we have an interval. Okay, an interval which suggests that we can also have a continuous word Markov process. Okay, any question? Any question? Okay.
Now, what I think we've talked about it too. We said things we need to know at the state space, which we've looked at already in class. Possible transitions, how we can illustrate transitions in a word problem, and then also how we can manage transitions in a word problem, and the transition probabilities, the one-time probability transition matrix. Then we can also look at the end state transition matrix, steady state transition matrix, or the initial state, initial state distributions of the process. Yeah, so we looked at this model in class as well. Okay, and we said that this is how Markov distributions are actually modeled. Okay, we call them the automation of the process. So a model of a particular system, we state 0, S0, S1, S2. Okay, so in this model, we can clearly see that we can move from S0 to S1. In other words, there's a path from S1 to S0 to S1, apart from S1 to S2, from S2 back to S1, S1 to S0, and then there is a loop back to itself. Okay, we also have a loop back to itself. Then we can also move from S2 to S0. We're all with various probabilities. So this is a kind of a weighted graph, weighted directional graphs, which gives us the probability of transiting from one state to the other. Okay. And like I said earlier, okay, so moving from a state can be represented as I or J. So we can basically write the transition probability from a state I, okay, to the state J as what? Pij. So if we have Pij, then we are saying that this is the probability of moving from a certain state I at the current time to a state J in the next transition.
Okay, so basically, this is how Markov models or Markov chain models are represented. Okay, you have the states of the process and the possible probabilities of moving from one state to the other. Okay, represented with a directional graph. Okay, so if you look at this chain tells us that we can move from state 0 to 1. We can remain in state 1 in the next transition. You see, all these things happen within equal time steps. Okay, they are based on the Poisson model and exponential time as we go ahead. You understand? So the equal time defined, okay, and arrivals for a Markov process must occur within these non-overlapping times. It means that if we are at S0 today, in the next transition, let's say that we define the time intervals as 1 hour. So in the next 1 hour, are we going to remain in S0? If yes, what is the chance of remaining there? That will be the loop back to itself. in the next 1 hour, are we going to move from S1 to S1, from S0 to S1? If yes, this is the probability representing that first transition. Okay. On the other hand, if we are in S1, there are about 3 possibilities. One is moving to S2 or S0 or remaining in what? S1. So if we are remaining in S1 in the next transition, what's the probability? That will be giving us what? P11. If we are moving to S2 in the next transition, what will be the probability? That will be P12. Okay. Then if we are moving from S1 to S0, what will be the probability? It will be what? P10. Okay. And then if you look at it carefully, okay, the transition probabilities are always written as Pij. Okay, they are written as Pij, meaning this I is where you are starting from and J is where you're going to end in the first transition. So if you are starting from S1, it will be P1, and then if you are ending in 2, it will be what? P12. Okay, good. If you are remaining in S1, then it will be P11 because you remained in the same what? In the same state. Okay, that is what this probability model is telling us. Okay, if there are any questions, please ask so before we move on. Okay, so let's move on.
Okay. Then we also have, this is an example of a Markov chain we looked at. So we have the probabilities and then the possible transitions in this state diagram. Okay. And then you are asked to determine the transition probabilities. And I think we looked at that also in class. We were very conversant with that. Okay, so we will not do much on that. All we said was to construct the transition.
Okay, so let's do that too here, because this is a previous class where we had already done something. So usually this model is represented with the first state transition matrix, which is Pij. Okay, and then we construct Pij using the possible states of the process. So in this weather forecast, which is X, okay, X has 2 possibilities: sunny day and a rainy day. Okay, so in constructing the matrix, you will bring the initial states, which is S and R, as your first column here. Okay, then you bring your matrix, and then on top of the matrix you have you repeat S and R. Okay, this is for future. Okay, so this is the first transition in the future, the next step. Okay, so we call this the one-step transition probability matrix. Okay, meaning today and then next step. So in representing this in the matrix form, this will be S to S. Now we are in sunny. Sunny back to sunny state will be what? The probability is what? 0.7. So you represent that here, 0.7. Then again, we have sunny. From a sunny day to a rainy day will be what? 0.3. Okay. Then when it comes to rainy day back to a rainy day is 0.4. Whereas from a rainy day to a sunny day is what? 0.6. Okay, good. Then one thing you have to take note of is if you are in a particular state, let's say a sunny day, then the probability of either staying in that state or moving out of that state. When you sum all probabilities, it should be equal to what? The sum of all probabilities from a particular state, okay, let's say PS to J. When you sum it up, you should get 1. So when you sum this probability here, PS to J means it can be in the state S or it can be in the state R in the future. That will be 0.7 plus 0.3. When you add, you get 1. And the same way from R to S is 0.6. From R to R itself is 0.4. So 0.6 plus 0.4 should be equal to what? Should be equal to 1. Okay. Now let's take another example. Yeah, so I think because of the breakages, we lost some time. The first 45 minutes is almost out. I have like 1 minute gone. 1 minute left. Okay. So once I go off, I'll start the class again. Just stay on. Okay, so let's take the next example. So if we are given a matrix, say Pij, which is giving us, let's take states 0, 1, and 2. State 0, 1, and 2. So take note of what I'm writing. So let's say we have probability 0.4, probability 0.5. Then we have probability here 0.3. This is 0. This will be 0.7. And then this is 0.2 here, 0.4. Now tell me